Lecture 6, we'll be talking about various kinds of sterilization methods, including heat-based, steam-based, gas-based, radiation-based, and bright light-based sterilization method. Okay. So number one, so what do we want to kill? So if we want to sterilize, we need to know what we are dealing with, right? So sterility is defined as the complete absence of microbial life. So microbials are mostly the enemies we need to kill. Okay, so achieving stability is the topic of this lecture, as you know. So then how do you kill those microbials? So microbials are susceptible to the exposure to heat, gas, some gas, radiation, strong radiation, and of course filtration will be trapping those. Okay, so when you deal with these topics, you need to know the definition of these terms, of course. Sterility means absolute freedom from biological contamination. So you eliminate them all completely, then you make the condition sterile. Okay, asepsis is a freedom from microbial infection potential. So infection potential is removed. That's what asepsis is, or aseptic. Okay, so if you use aseptic processing handling, that kind of reduces the chance of getting infection. That's what it is, right? And sterilization is a process of getting your sterility done and establishing your sterility. And disinfection is making object non-infectious by killing most of them, not all of them. Okay, sanitizing agent, of course, that's a chemical that reduces the microbial population. Spores are a resistant form of microorganism. They are hibernating form. They can stay around for a long time in a very resistant form, and then they can come back to life when the condition is good. And then they're resistant because they have very protective outer shell. It's like Bacillus or Clostridium species are a good example. And then vegetative cells are growing cells. Okay, cells that are capable of multiplying. They can grow. So vegetative cells can become spore forms when the conditions are not good. Okay, so if you look at this microbial life cycle, so these are vegetative cells growing and dividing, right? But so they can do that when there's enough nutrients, the conditions are favorable. But if the condition is not good, they can actually develop something called spores inside of them and then release them. So that released spores will maintain their life on the very harsh condition. Okay, it's a way of surviving for these bacterial cells. But when the condition comes back favorable, they become vegetative cells and live. So it's a kind of way of dealing with the harsh condition, evolution of bacterial cells, if you will. Okay, so spores are much more resilient to cope with the harsh condition. And vegetative cells, when they are growing, they go through this growth curve, as you know. So lag phase, when they're introduced, before they start growing, growing meaning dividing, right? Cells don't change their size. Actually, they just divide, multiply. That's what cell growth means. So when they divide, they grow exponentially, 2, 4, 8, 16. Okay, exponential growth. That's the growth phase. Okay, log phase, if you will. And then stationary phase, when cells kind of settle down because they run out of space, oxygen, nutrients. That's a stationary phase. They don't double, they don't divide anymore. So division phase, not dividing phase. That's adjusting before they start dividing phase, right? And if that stationary phase stays longer time, they will start to die. So death phase after that. Okay, so typically 4 phases will make up the bacterial growth. Microbial death kinetics, and how do you kill those cells? That's the thing. The bioburden is unwanted, undesirable microorganisms existing in your manufacturing space, right? How do you deal with them? Okay, so when you try to kill, you want to kill them efficiently, okay, by eliminating through log reduction. Log reduction is 1 log is 1/10, 2 log is 1/100, right? So that's the log reduction curve. And when you deal with this, you need to know microbial death, they are not killed instantly. It takes time, and death curves are exponential as well as the growth curve. And plot log of survivors versus antimicrobial exposure time. So the more longer time exposure cells that will be killed more efficiently, the slope will be the average death rate. That's how you can calculate it. So there are important values when you determine how successful your sanitization or the killing method is. You need to look at the D value, which is decimal point reduction value, okay, right here. What it is, the time or dosage required for getting 1 log reduction of your bacterial cells when they're exposed to your treatment. So that's the D value. So here's that, death curve. So death curve, and it's maybe time required to get the 1 log phase reduction from 10 to the 4th, 10 to the 3rd, 1 log reduction, okay. How much of treatment is required for that, okay? That's the, this is the D value, okay? It could be a temperature instead of the time, okay? Again, that could be a D value if that's the case. And Z value is increased temperature dosage unit required to reduce D value, okay? So D value is what the treatment requires to get 1 log reduction. If you show that in not instead of time, if you show that in maybe temperature or dosage or something different, that's going to be the Z value, okay? F value is the time at a given temperature that lethal amount of sterilization is delivered to a unit of production. So anyway, just understand, if you are a QC scientist or PD scientist, you need to understand what D and Z value is to determine the right temperature condition or dosage of your sanitizing agent and things like that, okay? And heat is one of the most efficient sterilization method, of course. Heat can effectively kill microbial cells. And then how do you generate heat? Do you use dry heat or wet heat? So if you use steam, you will consider that as a wet heat because there's a vapor, steam vapor, that's transmitting heat. So that's more efficient in transmitting heat. So actually steam is preferable, okay? So that's the sterilization method. Steam sterilization method is preferable for use for rubber, plastic material that is not melted, durable, and maybe like filter housing and filter itself, things like that can be steam sterilized. Mixing tank, equipment parts, freeze dryer chambers and things. Okay, so the bottom line is the more moist heat. The wet heat is more effective in transmitting heat instead of dry heat. Okay, so that's why you use pressurized steam when you try to sterilize instead of autoclave or when you do SIP, steam in place. And the steam in autoclave must be pure because if the water is not pure, the steam will be also not pure, right? So you want to use UFI when you generate the steam. Okay? And the temperature sensor or BIOT tapes are used to validate your steam in SIP process. How do you know the temperature you want to set is really reached during your sterilization cycle? So you need to probably place a temperature probe and see if you get that desirable temperature in there. Or BIOT tape is a kind of a cheap and quick way of validating. Okay, we'll talk about what it is. And the steam sterilization cycle involves preconditioning, okay, heating, preheating, and then the chamber will be heated up, and then loading, your material will be loaded, and then you're going to shut the door, and you will introduce the steamed heat in there and maintain it for about at least 15 minutes, and then remove the steam and release the vacuum pressure, and then take your stuff out. That's the process. And BIOT tape, as I said, it's developed by a scientist named Boy and Dick. That's why it's called Boy and Dick, BIOT tape, in 1963. So it uses a chemical indicator to detect the presence of air due to the air leak or inadequate air removal and the steam penetration. So the thing is, so there is a kind of steam sensitive indicator ink here, okay, on this tape. So if this tape is exposed to the steam heat, it changes the color. So before exposure it may look like that, and after exposure it becomes like different color. Okay, so if you place this tape on the material that should be steam sterilized, then see if this this tape will change its color to this. If it doesn't change, that means there isn't enough heat steam introduced in your chamber. So that's what it is. Okay, so it's a simple validation method, but it's not a kind of GMP method. So they don't acknowledge this. This is too cheap. And this is the design of an autoclave machine where you will use steamed heat inside of this chamber, and the steamed heat is maintained at least like 15 minutes, and then things will be killed. Okay, so steam in place or sterilization in place, that's SIP. If your instrument is too large, you cannot place it inside of the autoclave, then how do you sterilize it? Then you have to place a steam generator inside of the instrument and then sterilize it that way, right? So this is following after CIP, clean in place. Okay, like think about a huge bioreactor, like a 2,500 liter bioreactor. It's like 2-story tall. And how do you sterilize it? You do the CIP and SIP. Okay, so you clean it first, and then introduce steam generator and make sure all the valves and everything is closed, and then do the sterilization method. Pressure versus temperature. Okay, so temperature and relations in autoclave. So 5 psi at that temperature, and 10 psi, 30 psi at the temperature. So complete replacement of air by steam. What it's showing is if you pressurize the chamber in the autoclave, you will get a higher heat effect. That's what it is. As the pressure is going up, since the steam vapor is pressurized, you get a higher heat effect. So that's what it shows. Okay. If you do not use steam heat, if you use dry heat instead, okay, dry heat can also kill microorganisms through oxidation. Okay, but since dry heat is transmitted much less efficiently, you have to use higher heat, like 170 degrees or above is required. Okay. So glass oil, metal pots, oils, heat-resistant dry powder, they can be dry heat sterilized. So, for example, like depyrogenation method. So you can remove endotoxins using dry heat. In that case, you need 250 degrees Celsius. Okay. So anyway, it requires longer exposure time because the heat transmittance is less efficient. So dry heat sterilization cycle time. Rate of heat to 320 degrees Fahrenheit exposure period. Okay, so it takes this time to reach the temperature. You maintain it this long. That's what it means. Okay, so if you're in an autoclave, these different things, you need the requirements. That's what it shows. Okay, so the heat is one of the efficient sterilization method. And next one is gas.